Welcome back to the module on dynamic approaches for AutoML. In this unit, we are finally talking about dynamic algorithm configuration by reinforcement learning. For that, recall that in the RL background section, we discussed how an agent learns by interacting with an environment. However, in the DAC equivalent, an environment means that we have an algorithm that is solving a particular data set. And we don't want to learn configuration policies that only work for a particular data set. So RL in general is not set up with generalization in mind. So to be able to learn general policies, we need to leverage the contextual MDP and slightly modify the policy as well as the training behavior. To learn general policies that take into account that we have different data sets, i.e. the context, we can choose two different approaches. Context oblivious policies only observe the current state of the algorithm that is being tuned, and they generalize by learning across a distribution of datasets, right? So you see a diverse exposure of what the state and action mapping actually produces in terms of rewards. So you learn potentially a policy that works well across this distribution, but not necessarily one that works optimally at every element of this distribution or every element that you can draw from the distribution. These policies are robust and tolerate variation, but like I said, they are not really set up to adapt to a specific data set. But they are very easy to realize because you only need to sample different environments during the training procedure rather than having any change to the policy at all. Counter to the context oblivious policies, we have context aware policies, policies that explicitly take the context into account, right? They are conditioned on the context and they are able to observe certain meta features that tell us something about the context, something about the environment. They can directly adapt to the specific data set at hand. So if we have two potentially very different data sets, our policy can also behave very differently in these two data sets or in these two environments. However, you need to make additional design decisions to make them work well. So for example, one question that you need to ask yourself is, what is even an appropriate context here? And if you know what an appropriate context is, you need to make a decision on how to best incorporate the context into the learning process. And the reinforcement learning researchers are making quite a lot of moves in this direction. Now, on the action side for DAC, we could either directly set the hyperparameter value by taking the action. That gives us a full flexibility for adaptation, but this can give you very, very bumpy schedules. And in reinforcement learning, you would call this bang-bang control. If your learning rate is always bouncing up and down like this, it's not necessarily the best behavior that you want to induce. So instead, what you can do are relative updates, where you change the hyperparameter, for example, by a factor, where you take the previous hyperparameter value and perturb it or modify it or multiply it. And that gives you slightly less flexibility in terms of how to adapt the hyperparameters, but it also results in much less bumpy schedules. The states for DAC should start with everything that is already used for designing heuristics manually, because that is very informative. That is how many humans themselves would adapt the algorithm on the fly. So for learning rates, that could include the previous learning rates, the number of updates that have already happened, the observed loss, the momentum, if you have a momentum in your optimizer as well to potentially counterbalance that, some other form of gradient information based on which you might want to make a certain decision. Now, why are these good features for something like dynamic algorithm configuration? Well, they are very informative and usually, like I said, are used already in these manually designed heuristics, which are designed purposely to do this task. So those are well-tested informative state features. They are available in most existing implementations, so they're easy to access, cheap to compute, they don't include a lot of overhead, and often they quantify the progress of the algorithm that you're tuning, at least in some form. If these state features are very, very noisy, you might want to smooth over them for a few steps because your reinforcement learning agent is set up to react to an observation, right? And if it reacts to all of these small noise changes, you might again induce a very bumpy schedule, which you might not want to have at all. The transitions are implicitly given by the training algorithm, and it's just the iteration for one step, for example, with a given hyperparameter setting. but the granularity with which you observe these transitions can be very important. So if you observe too often, it can make it very difficult to learn anything at all. If it's too infrequent, you might miss crucial points where you actually want to update your algorithm. So you might not necessarily set them to the best hyperparameter values accordingly. But if you assume that your hyperparameters can stay constant for some time, right, you can also make use of more dedicated RL approaches that really try to learn not only what action to take in a state, but also how long to commit to a certain action. Now, talking about the rewards, while it might sound simple, it's important to call out here. In AutoML, we minimize costs, but in RL, we maximize rewards, right? So you really, while it's a super simple design decision here, you need to take it into account that the reward should be at least the inverse of the cost. Now, RL agents optimize a cumulative reward. That means we go quickly for better cost values during the training, which is often fairly well correlated with final losses. But it's fairly greedy, right? That can lead to very aggressive hyperparameter changes early to minimize costs quickly, but not necessarily take into account what happens later on. That could potentially be addressed with some hyperparameter tuning on the RL side to determine what the horizon should be or like how far you should discount in the future. But that is not always a silver bullet, and tuning on top of tuning is a very expensive procedure. We have already discussed a little bit about context awareness for our policy to learn more adaptable behavior. And one thing that we could do is let the agent implicitly learn what kind of dataset it is actually dealing with right now. That is possible if you have a very large history of observations, because then you can see how different your traversal through a state space might be. But these histories require potentially much more training if you have a large history. So while it is possible, it's not necessarily advisable. If you provide meta features directly characterizing the dataset, usually you can make a lot of use of existing features, such as counting features that tell you something about the number of classes or related elements in the dataset, or landmarking features where you know how a simple model, for example, behaves on this particular dataset. The simplest approach here is, if you have these meta features at hand, is just concatenate them to the observation for your reinforcement learning agent and just make decisions based on the observation of the state and the observation of these meta features. This super simple approach can often already outperform context-oblivious policies, but the most appropriate context might be still problem-specific. And to summarize, you should know that context-oblivious policies can learn robust and generalizable behavior by learning across a distribution of environment contexts. Context-aware policies, on the other hand, directly adapt to the dataset, but require careful additional considerations, which might make them a little bit more tricky to set up. And last but not least, dynamic algorithm configuration by reinforcement learning is one of the most powerful approaches for dynamic tuning, but requires potentially much more compute, because you first need to learn your policy such that you can then later on optimize your other algorithms or your algorithm runs much more efficiently.